All right, this is the full-blown banked turn problem where we actually have friction involved as well. So here's my overhead view. I have a car turning in a radius of 35 meters, and I'm told that it's on a banked turn. I can't view that from above, so I need a second diagram in a second. And I have a static friction coefficient of 0.8, and I'm trying to figure out how fast can they go through this curve without slipping. So the standard procedure here is to view the car from behind. So I just drew an eyeball and I'm looking at the back of the car and I want a new perspective. So I'm going to draw my bank turn. 10 degrees isn't even that much. It's a pretty shallow angle, but I want it to be steep enough to make diagramming easy. All right, there's the wheels. So that's what I see from behind, and I'm going to go ahead and get a reference to the horizontal in here so I can show the angle of incline is 10 degrees. And I'm seeing this thing accelerate to the center of curvature. So let's put that in the diagram. This is just a geometric fact. To move in a circular path with radius r at a speed of v, the acceleration must point toward the center of curvature to get that done. From this point of view, that's just to the left. So my acceleration goes exactly to the left. Okay, and one qualitative thing I should say here is I noticed the car doesn't change its height at all. The acceleration is purely horizontal, so there is no going up or down. This suggests to me that rather than using a tilted coordinate system, the natural coordinate system for the problem is horizontal vertical. Because I have zero acceleration in the vertical direction, 100% of it in the horizontal direction, this is going to be the most useful set of coordinate axes. All right, then I can start to get forces into the problem. It's our old friend gravity always pulling down. Very predictable. All right, and there's no decomposing gravity into components for this problem because it's perfectly lined up with one of the coordinate axes. Then I have a normal force of the road pushing. So the road can exert parallel and perpendicular forces. The perpendicular one is called the normal force. And I'll just label it like that. The parallel force that a surface can exert is the friction force. I've got to figure out which way the friction force points. So when I see this maximum speed without slipping, I'm thinking, oh, I have a static friction force that's going to be at its maximum value. It's about to give up. So which way is this static friction force pointing? One way to think of it physically is just to take it to the extreme. Ask yourself what happens when this car slips. And if I went through this corner way too fast and slipped, I would go to the outside of the curve. Now, from a distant perspective, I can say I'm really going in a straight line, but from this behind the car perspective, I'm going to say the car flies off the road that way if the friction force gives up. That means the friction force must be pointing this way. And again, that's always parallel to the surface. Go ahead and put that back in. So I'll call that little Fs. And we know the static friction force, if we're looking at the maximum speed before slipping, the static friction force is maxed out, and we'll put that into our equations later. All right, we've got to find some angles here. So I'm looking at this familiar picture. I have a perpendicular to the surface, and we figured out previously that the angle of incline of the ramp, I'm just going to get rid of that real quick to make it easier to look at. The angle of incline of the ramp is equal to that angle right there. But these two angles are congruent. So this is also 10 degrees. All right, so there's that piece. Then I can look at this angle right here. And I noticed that this is an alternate interior angle with this one. So I have a line. I have two parallel lines intersected by a third line, and it makes those interior angles congruent. Old geometry stuff from long ago. So that's also 10 degrees. This allows me to begin decomposing into components, putting everything into this vertical horizontal coordinate system. So I have an upward component of the normal force. That's going to be n cosine of 10 degrees. I have a component of the normal force pointing to the center of curvature. This is a good thing. I know the net force must point in that direction. So I better see at least one force pointing that way, otherwise it's not going to work. And I'm going to go ahead and, I suppose that's enough room. So that's an n sine 10 degrees. And then my friction force is interesting. It doesn't point straight to the center of curvature. It points down a little bit. So part of that is pointing to the center of curvature. And that's going to be Fs cosine 10 degrees. And then the other part points down a little bit. And that's going to be an Fs sine 10 degrees. All right, this is starting to look pretty complete to me, but it can be overwhelming. That's a lot going on in a force diagram. So let's just start setting up our x and y analysis using Newton's second law. So I'm going to do the y analysis first. Look at F net equals ma along that direction. And so there is no acceleration vertically. The car constantly stays at that same height as it goes around the corner. So the right-hand side of this is 0. And that simplifies to just saying the net force in the y direction is 0, or the sum of all the upward forces must be equal to the sum of all the downward forces. If you want to just jump straight to that, it's perfectly fine. So I have n cosine 10 degrees. That's my upward force. Has to be equal to the sum of the downward forces, which is Fs sine 10 degrees plus mg. And we're just going to keep that in that form for now. I actually have to move to a second page to finish the calculations on this problem, but that's where we're at right now. Our x analysis, F net in the x direction is equal to mass of the car times a in the x direction. My acceleration is right here, center pointing, and I'm going to call that the positive direction. And I have two contributors to the centripetal force here, to the net force that's causing the centripetal acceleration. And one of them is n sine 10 degrees, and one of them is Fs cosine of 10 degrees. All right, so that's going to be equal to the mass times the acceleration toward the center, which is v squared over r. So that's my second useful equation. I'm going to modify these just a little bit before we get into grinding through all the algebra here. I need to get in the piece of information here that the friction force is maximized when we're at the maximum speed before the brake loose. So that means Fs equals, so Fs max is going to be mu s times the normal force. This one too. All right, and that means the V we're talking about here would be V max. So let's make those modifications. I'm going to put a brace on this so it looks a little more like we're just doing an algebra problem, because that's what it's about to become. So, oops, that's not a kinetic friction. Mu s n sine 10 degrees plus mg. And then in my x direction, I have n sine theta, or sine 10 degrees, plus mu s n cosine 10 degrees equals m v max squared over r. So if I stare at this for a second, I think, what are the knowns and what are the unknowns? And the normal force is unknown, but I'm also not interested in it. So I'm going to find a way to eliminate that. That's going to be my strategy. The mass is not known, and I'm going to hope that that cancels out. And then V max is not known, and it's what I want to solve for. So we'll get to that on the next page. Here's where we left off. And again, I want to eliminate n, and so what I'm going to do is move all the n containing terms to the left-hand side of both equations. So here's our next iteration, and I have n cosine 10 degrees minus mu sub s n sine 10 degrees equals mg, and the bottom one is already done for me, n sine 10 degrees plus mu s n cosine 10 degrees equals m v max squared over r. Then I'm going to factor the n's out, and I get n times the quantity cosine 10 degrees minus mu s sine 10 degrees equals mg, and I have in the second equation n times the sine of 10 degrees plus mu s cosine 10 degrees equals m v max squared over r. So these equations have a nice symmetry to them. What I'm going to do here to make my life as easy as possible is I'm going to take the bottom equation and then divide it by the top equation, because that puts v max into the numerator of the result and it makes it easier to solve for it. Then I know that's what I'm going for. So I take the bottom equation again and divide by the top equation. So I end up with n times the sine of 10 degrees plus mu s cosine of 10 degrees, all divided by n times the quantity cosine 10 degrees minus mu s sine 10 degrees equals m v max squared over r, and then I divided that by mg, so that puts an m and a g into the denominator. And there's the moment where my m's cancel, so the mass of the car doesn't matter. The n's cancel, which I'm happy about just because I'm not interested in calculating it. And then all I have to do is multiply both sides by gr and take the square root. So I'm pretty much there. I have v max is equal to, let's see, I had gr sine 10 degrees plus mu s cosine 10 degrees over cosine 10 degrees minus mu s sine 10 degrees, all square rooted. And it's time to plug in numbers. So this giant square root, 9.8, 35 for the turn radius, sine 10 degrees plus 0.8 for the coefficient of friction, cosine 10 degrees, all divided by cosine of 10 degrees minus 0.8 sine 10 degrees. And I smashed these numbers prior to recording this, and it came out to 19.7 meters per second maximum speed before breaking loose on this banked turn. If you compare that to the maximum speed on the corresponding unbanked turn, it's a larger possible speed without breaking loose. That's the whole point of banking. And then if you're curious, I just converted units. Instead of doing unit analysis, I just did a Google search just to put it into more familiar units. Turns out to be 45 miles per hour, 44 miles per hour. All right.